So good afternoon, everyone, and welcome to this class. This is a brand new topic, and this is magnetic effects of current. How does current create magnetic effect? Now, before going into magnetic effect of current, am I audible and visible to all of you? You can hear me? Can see me? Because I can't see any one of you. Anyone is there? Anyone can see me? Yes or no? Everyone can see me. No, you can see me. You can hear me, right? My other device is not working, so I can't see you.
So your video is getting stuck, sir.
Tarnaka, Chintal, are you able to get me? Chintal, Tarnaka, are you able to hear me? Get me?
Your video is getting stuck. Sir, start.
Okay. So, in this class, we will start magnetic effects of current. Now, to understand magnetic effects of current, you must understand what is a magnet. What is a magnet? Anyone knows? Anyone knows what is a magnet and what does a magnet do? Anyone knows what a magnet is and what a magnet does? Yes or no?
Sir.
Every magnet has two poles. One pole is known as the north pole and one pole is known as the south pole. Yes or no? Sometimes we can refer to as north pole as positive and south pole as negative. We all know this. Every magnet has a pole strength. The pole strength of the north pole is known as plus M, and the pole strength of the south pole is known as, we call it as minus M, because we call the north pole as the positive pole. It's plus M and minus M are the pole strength of a magnet. This type of magnet is known as a bar magnet. Instead of calling it as a bar magnet, you can always call it as magnetic dipole. Do you understand the meaning of magnetic dipole? Have you heard this term, magnetic dipole?
No, sir.
It has two poles. Both the poles are magnetic in nature. We can call it as magnetic dipole. We understand this?
Yes, sir. Yes, sir.
Every magnet has a length. The total length of the magnet is known as Lg, geometric length, end to end, geometric length. But these poles are not at the ends, they are somewhere inside the magnet. The distance between the two poles, if north pole is here and south pole is here, the distance between these two poles is known as Lm, the magnetic length. Do we understand this?
Yes, sir.
Draw it. Have you drawn this, everyone?
Yes, sir.
Okay. Now, we have heard the term electric dipole, yes or no?
Yes, sir.
Every electric dipole has an electric dipole moment, yes or no?
Yes, sir.
The electric dipole moment is from negative to the positive terminal, yes or no?
Yes, sir.
Similarly, a magnetic dipole moment is from south pole to the north pole, and this magnetic dipole moment, I am doing it in short because I think you already know this. Magnetic dipole moment M is given by this M into L, magnetic length, and this magnetic length is actually taken as a vector. It's known as a dipole axis, and it's from south pole towards the north pole. Do we understand this? This ratio of magnetic length to the geometrical length for a magnet of an electric dipole is somewhere around 0.84. Everyone understand this? Every magnet is characterized by a magnetic dipole moment. Whenever we talk about magnet, we do not talk about pole strength, we do not talk about the length, we only talk about the magnetic dipole moment. We understand this?
Yes, sir.
Every magnet creates magnetic field. What is a magnetic field? Yes, every magnet creates magnetic field. What is a magnetic field? It's a region in space. What was electric field? How did I define electric field? Yes, anyone remembers it? Electric field, anyone remembers what? How did we define electric field? We are done with this. Yes or no? Just say yes or no. I can't see you, so say yes or no. I'll move ahead. We remember what was electric field? How did I define it?
Produced by a charge, sir, in space.
Yes, it was. Okay. Magnetic field is a region in space where a magnetic pole experiences a force. If you have a magnetic pole and it experiences a force, that region in space you will have magnetic field. Now, how strong is that magnetic field? We call it strength of magnetic field or magnetic field intensity. Strength of magnetic field or magnetic field intensity. Strength of magnetic field. Strength of magnetic field or magnetic field intensity. Strength of magnetic field or magnetic field intensity is denoted by the letter B, and it is a vector. This is force per unit M. Here M is not the mass. Here M is the magnetic pole strength. Here M is the magnetic pole strength. Magnetic field is a vector quantity. Magnetic field is a vector quantity. And to find out the magnetic field, the strength of magnetic field, you place a magnetic pole, you find out the force. If this is your magnetic pole plus M and it experiences a force F in this direction, the magnetic field strength at this point will be F divided by M. We understand this?
Yes, sir.
magnetic field or magnetic field intensity or magnetic flux intensity. The SI unit of magnetic field, the SI unit of magnetic field is Tesla, capital T, or you can also call it Weber per meter square. Tesla or Weber per meter square. Find the force on a magnetic pole. You can find the force on the magnetic pole F vector as m times b vector. Remember, m is not the mass, m is the magnetic pole strength. Do we understand this? Yes or no?
Sir.
North pole will experience force in the same direction same as the direction of magnetic field. North pole is just like a positive charge. You can take it as a positive charge. So it will experience force in the same direction as field. A negative charge is not negative charge here. Negative pole, there is no negative pole here. South pole will experience force in the opposite direction as that of the magnetic field. We understand this? Everyone understands this?
Yes, sir.
Now this magnetic field is somewhat different to an electric field. When we talked about electric field, we told you that electric field starts from somewhere and ends somewhere. Where does an electric field start from? Electric field has a starting point, electric field has an end point. What is the starting point of an electric field? From where does an electric field start? Anyone can tell me that? It starts from a where?
Negative, sir.
PD.
Positive to negative.
Yes. Uh, electric field starts from a positive charge and ends on a negative charge. Electric field has a starting point and an end point. But magnetic field does not have a starting point, does not have an end point. Magnetic field B is in closed loops. Magnetic field B is in closed loop. No starting point, no starting or end point. Magnetic field is in closed loop. It does not have a starting point. It does not have an end point. This is one way of saying it. Now, whenever we have drawn, have you seen the magnetic field of a bar magnet? Have you seen the magnetic field of a bar magnet? Anyone has seen magnetic
Yes, sir.
field of a bar magnet? Now, if I draw the magnetic field of a bar magnet, this is a bar magnet. This is the north pole. This is the south pole. The magnetic field, I draw it by magnetic field lines. It goes like this. Have you seen it? Yes or no? Have you seen it?
Yes, sir.
This is the best that I can draw. Now, it is always going from north to south. Do we understand this? It is always going from north to south. But as I told you, the magnetic field lines are in closed loops. So not only do they go from north to south, they go from north to south, outside the magnet, inside the magnet, they are going from south to north. Do we understand this? So this is how the magnetic field lines of a magnet is. Magnetic field lines are always in closed loop. They don't have a starting point, they don't have an end point, they're always in loops. The other way of saying this is magnetic monopoles do not exist. That means magnetic monopoles do not exist. That means you cannot have a single north pole and you cannot have a single south pole. Wherever there is north pole, there is south pole. Wherever there is south pole, there is north pole. You can cut magnet into infinite pieces, but you will never get one pole. You can have a single positive charge, a single point charge is possible. A single negative charge, point charge is possible. Electric monopoles exist. Electric charge can exist without pairs. A positive charge can exist on its own. A negative charge can exist on its own. But a north pole cannot exist without a south pole. South pole cannot exist without a north pole. Magnetic field lines have to be in closed loop. All mean the same thing. We understand this?
Yes, sir.
Everyone understands this? Have you written this down?
Yes, sir.
Yes, sir.
You see, I can't see you, so you will have to let me know. Otherwise, I will be stranded. Now, whatever we are going to study about this magnet is analogous to what we had done for electric field. The only problem is we don't have a single pole. We had a single positive charge there, but we don't have a single pole here. Anyways, otherwise
Sir,
everything is exactly same. Yes, beta,
why monopoles don't exist, sir?
they don't exist.
Why?
They don't exist. Why charge exists on its own? It exists. Magnetic field due to a monopole. Though monopoles do not exist, but we can find out the magnetic field due to a monopole. Now, what is the magnetic field due to a monopole? If I have a monopole which does not exist, and I let me call it as plus m, that means I'm calling it as a north pole. I have a point P which is at a distance r. I have a point P which is at a distance r. Now, this north pole or this positive pole or this positive monopole which does not exist creates a magnetic field at this point. The direction of that magnetic field is like this, P vector. It is along the line joining the monopole to the point and it is moving away. Does it remind you of anything? Does it remind you of anything? Does this remind you of anything from the past?
Field due to point charge.
Electric field due to a point charge. So let me draw it here so that you understand that we are probably doing the same thing but in a different way. The only difference is I don't have a monopole existing. This gentleman creates an electric field. Does anyone remember the formula of this electric field?
KQ by R square.
Do not call it as KQ by R square. The actual form, assuming that it is vacuum. The electric field E, direction I have already drawn, so I'm just writing the magnitude, is Q by 4 pi epsilon naught R square. We understand this?
Sir.
Magnetic field here, and you will find some surprising things, is mu naught by 4 pi m by r square. Does it look familiar? That is what you have to understand. wherever epsilon naught comes in the denominator, mu naught comes in the numerator. And apart from that, you can see everything is similar. Yes or no? One thing also you must know that mu naught into epsilon naught is actually 1 by c square, where c is the speed of light. This is how all these terms are related. This is a magnetic field created by a monopole which does not exist. Now, if you know the formula for this monopole, and you can see that this formula is exactly same as point charge, you can find out the other formulas as well. Everyone understands what we are getting into? Yes or no? No or yes?
Yes, sir.
Yes, sir.
Pakka?
Pakka, sir.
Okay. Now, does anyone remember the formula? Okay, remember here magnetic monopoles, as I told you, do not exist. So there is no point of remembering this formula because you will never get a question where you will have a single monopole. Yes or no? The only thing that makes sense is when it is not a monopole but it is a dipole. Do you understand what I'm saying? Only thing that will make sense
Yes,
is
sir.
when it is a dipole. Yes or no?
No, sir.
Are you able to get what I am telling you, beta? You can only,
Yes, sir.
because electric monopoles don't exist, so there is no point of doing any question on electric monopole because it does not exist. We have just seen the formula because we wanted to see the relation between a monopole and a point charge. That was the only reason we did this formula. There is no point of going any further on this. The only thing that makes any sense would be how are we going to use these monopoles? Monopoles are do not exist. So we'll have to go into a dipole. So the next heading is magnetic field due to a dipole. 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 Can anyone tell me what will be the formula of magnetic field due to a dipole? Instead of calling it as a dipole, I am going to call it as a bar magnet. Magnetic field due to a bar magnet. Magnetic field due to a bar magnet. Now, this formula should remind you of something that you have already done. Does it remind you of something that you have already done? This formula, this diagram, does it remind you of something that you have already done? Yes or no? Does it remind you of anything? Does it remind you of anything, beta? No?
Field due to concentrate equatorial position.
Electric field due to electric dipole at equatorial position. Does anyone remember the formula of electric field due to a dipole? If the distance is large, at the equatorial, at the axial, this is the axis. This one is the axis. And this one is the equatorial line. The other one is the equatorial line. One is the axial line. Anyone remember the formula? Yes? Electric field vectorly.
Into R sin theta.
Huh? K into R sine theta. No. Was 2k p vector by r cube. And it is in the direction of the electric dipole moment. 2kp, where k was 1 by 4 pi epsilon naught. So it basically becomes 1 by 2 pi epsilon naught p vector by r cube. Do we remember this on the axial point?
Sir.
Okay. Now, since we know this electric field, can you now tell me the formula for magnetic field? What will be the formula for magnetic field on the axial point?
Mu naught by 2 pi into p vector.
P by R cube, sir.
Mu naught by 2 pi into not p vector m vector by r cube. Or sometimes it is written like this: 2 times mu naught by 4 pi into m vector by r cube. We write it in this way so that it looks similar to this one. Okay. What was the electric field?
Yeah.
And
Video and audio is not clear, sir.
Yes, beta.
Sir,
Sir.
you are stucking.
Yes, beta.
Not clear. Your video is stucking. Lagging.
Okay. So is it okay now?
Sir.
No, sir. Sir, will you rejoin again?
Sir, once rejoin.
No, it will not happen. I mean, it will not work that way. Now, if I rejoin, is it getting stuck? Let me see.
Yes,
If I,
sir.
so we were discussing the axial electric field, and we can also write the formula for equatorial field. What was the formula for equatorial electric field? Can you tell me, anyone?
Yes, sir. KQ by R cube.
Hmm?
KP by R cube.
It should be written in this fashion: minus kp vector by r cube, because it is in the opposite direction. Yes or no?
Yes, sir.
And write it as 1 by 4 pi epsilon naught p vector divided by r cube. Similarly, I can write the magnetic field in the equatorial region perpendicular bisector as mu naught minus mu naught by 4 pi m vector by r cube. We get this? Yes or no?
Yes, sir.
Okay. Now you can write the formula for a general point. Have you noted this down? I'll give you 2 minutes. Note it down. Then I'll give you the point for the general form. And remember, it is same for both. Give you 2 minutes. Note it down. So then, what we can do is we can write the formula for magnetic field due to a bar magnet at a general point. It will have two components, BR and BN. We understand this, everyone? Yes or no?
Yes, sir.
Okay. The electric field at a general point, the value of electric field at a general point was given by this formula Kp root over Kp by r cube root over 1 plus 3 cos square theta. Do we remember this?
Yes, sir.
What will be the formula for magnetic field at a general point?
Epsilon by 4 pi m by x cube root over 1
Mu naught m by 4 pi r cube
r cube.
root over 1 plus 3 cos square theta. We understand this, everyone?
Yes, sir.
Okay. Now, you must also think about this point phi, this angle phi. And in both the cases, can you tell me what is the value of this angle phi, tan of this phi? It's
1 by 2,
all
1 by 2 tan theta, sir.
1 by 2 tan theta. So remember this, draw this diagram, remember this, and let me know once you are done. Okay, then let's resume. You must understand that everything that we are doing here is same for whether it's electric dipole or it is magnetic dipole. The next heading is magnet or magnetic dipole in a magnetic field. So write the heading magnet in a uniform magnetic field, and you can draw. First listen to me, then I will give you time to draw and write bar magnet in a uniform magnetic field B. Now this is similar to electric dipole in a uniform electric field. Do we understand this? You understand this? Can you hear me? Can you see me?
Yes, sir.
Please say, please. I'm getting network problems, that's why. Okay. So when you place a bar magnet in a uniform magnetic field, the magnetic force acting on the bar magnet would be 0. Do we understand this?
Sir.
But the torque will not be 0, and torque will be given by m cross b vectorly. If I talk about the magnitude of torque, it will be given by mb sine theta, where what is theta? Theta is the angle between the magnetic field. As you can see, this is the magnetic field and this is the magnetic dipole moment. Theta is the angle between the two. We understand this?
Yes, sir.
This one is magnetic field and this one is magnetic dipole moment. Everyone understands this?
Yes, sir.
Now the same thing, I will write the formula for electric dipole in a uniform electric field. The electric force acting on the dipole would be 0. The torque acting on the dipole will be given by P cross E. The value of torque in magnitude will be given by PE sine theta. Everyone understands this?
Sir.
Yes or no? No or yes?
Yes, sir.
Okay. Now, the value of this torque, if we talk about the value of this torque is 0 at t. Oh, this torque is 0 when the angle is 0 or 180 degrees. Do we understand this?
Yes, sir.
this 0 degree angle, the 0 degree angle is known as the condition of stable equilibrium. Do we know this? The 0 degree wala condition is known as the condition of stable equilibrium, and this 180 wala condition is known as unstable equilibrium. Have you heard these terms, stable and unstable equilibrium?
Yes, sir.
Shabash. Stable equilibrium, unstable equilibrium. This torque, what is the maximum value of this torque? The maximum value of this torque happens at 90 degrees. And the maximum value of this torque is how much? M into B, or I can write P into E. I'm writing them together. Everyone understands this? Yes or no? No, yes.
Understood, sir.
One more thing that you have to understand here is the energy of a dipole in a magnetic field or an electric field, that is given by the formula minus mb cos theta or minus pe cos theta. Everyone understands this?
Yes, sir.
You can write it vectorly in this form, minus m dot b or minus p dot e. We understand this?
Yes, sir.
Just keep on saying yes, sir, so that I can just move on. At theta is equal to 0 degrees, u is minus mb. This is the minimum value. Minimum value means maximum stability. We understand this? At
Yes,
theta
sir.
is equal to 180 degrees, u becomes maximum. Maximum value is plus mb, and therefore it is known as unstable equilibrium. I'll give you now 2 minutes for you to note it down. If you have any doubts, you can ask them now. Okay, then we move ahead. We had seen this torque on a bar magnet or electric dipole. We have seen the formula of this torque. Now remember, the 0 degree is the position of equilibrium, stable equilibrium. So this torque, I'll now start the camera, see if, I hope it's not lagging now. It's not lagging. So what happens is this torque will try to bring, if you disturb this bar magnet from its equilibrium position, this torque will try to bring it back to the equilibrium position. Do we understand this?
Yes, sir.
Now, if theta is small, I can write this torque as m into b into theta, and it is trying to bring it back to its equilibrium position, and therefore the motion becomes simple harmonic motion. This motion can be taken as a simple harmonic motion. Do we understand this, what I'm saying?
Yes, sir.
You can find out the omega for this motion, and I will not get into the theory of simple harmonic motion because I know that you have just done it. It will be m into b by I. If it is a bar magnet, it will be p into e by I ka root if it is a dipole. Time period will be 2 pi by omega.
I by 4, sir.
So you can now find the formula. So remember, if such a question comes, this is a question which I call mixed question from mixed topics. SHM is mixed with magnetic field or SHM is mixed with electric field. I hope you can deal with this question now. Yes or no?
Yes, sir.
Okay. Do we understand this? I'll give you a couple of questions. Now remember, the question may be given in terms of magnetic field, but the same question can be made for electric field also. Do we understand this?
Yes, sir.
You have noted down this one so that I can move ahead with the question.
Done, sir.
Done, sir.
Well done, sir. Good. This is the question that you have to do. There is a reason why I have given you this question. 2 questions, and we will cover the entire electric dipole and magnetic dipole or bar magnet. A bar magnet having a magnetic moment, as I told you, whenever we talk about bar magnet, we talk about the magnetic moment. A bar magnet having a magnetic moment of this joules per Tesla. Remember this unit, joule per Tesla, is free to rotate in a horizontal plane. Horizontal magnetic field B exists in space. Find the work done in rotating the magnet slowly from a direction parallel to the field, which is stable equilibrium, to a direction 60 degrees from the field. Take a deep breath. Try and understand the question. I'll give you 2 minutes. If you're not able to solve it in 2 minutes, I will tell you how to solve it. 2 minutes you have to tell me how this is done. Whenever they are saying to move slowly, that means the change in kinetic energy is 0 and the work is done by the external force to move it slowly. So you have to find out the work done by the external force. Do we understand the question?
Yes, sir.
2 minutes you have to give me the answer. 0.2 joule should be the answer. I'm not worried about the answer. I'm more worried about the concept. And that is what you need to understand, because when the question comes in the exam, it might have both the option plus 0.2 and minus 0.2. Now remember, work done by the external force. Work done by external force in moving an object from point A to point B. Oops. And I must have told you this sometimes in the electrostatic field also, that will be equal to change in potential energy UB minus UA. Do we remember this? This is when the change in kinetic energy is 0. Everyone remembers it?
Yes, sir.
That's it. So energy at point B is minus MB into cos 60 minus MB into cos of 0. So the answer is MB by 2, and that is the answer that I was looking at. Everyone got this answer?
Yes, sir.
I'm only worried about the concept that it should be UB minus UA. If you understand that concept, there is nothing that has to be done in this question. One more question to wind up this topic, and we have done it quite nicely. Everyone has understood? Everyone has got this? Can I move on?
Yes, sir.
Yes or no?
Yes, sir.
This is the next question. I think you can see it on your screens. Yes or no? A magnetic dipole moment M is released in a uniform magnetic field B from the position as shown in the figure. Find its kinetic energy at theta is equal to 90, its maximum kinetic energy during the motion. Will it perform SHM or oscillation or periodic motion? What is the amplitude of the same? I'll give you 2 minutes to give me the answer. Everyone has understood the question, yes or no?
Yes, sir.
You have 2 minutes to give the answer. So how are we supposed to do this one? Well, we can do this in many ways. Let us first try to do number one. The black position is the initial position, and 90 degrees. Let me call this as position number 1, and let me call this as position number 2. We can do it by the law of conservation of energy. Total energy at point A, you can apply log में. Total energy at point 1 is equal to total energy at point 2. What is the total energy at point 1? Total energy at point 1 consists of magnetic potential, magnetic energy plus kinetic energy that must be equal to magnetic energy, magnetic potential energy plus kinetic energy at point 2. What is the magnetic potential energy at point 1? Minus mb into cos of 120. Do we understand this?
Yes, sir.
Kinetic energy at point 1 is 0 because it is at rest. What is the potential energy at point 2? The angle is 90, so it is 0. Yes or no?
Yes, sir.
Plus the kinetic energy at point 2. From here, you will get kinetic energy at point 2 is mb by 2. Do we understand this?
Yes, sir.
Now, where will it have maximum kinetic energy? Where will it have maximum kinetic energy? Can anyone tell me? Where will the kinetic energy of this particle be maximum? It will be maximum when it passes its position of equilibrium. Yes or no? Simple harmonic motion. Think about simple harmonic motion. Any oscillation, the particle when it passes its mean position, stable position, it has maximum kinetic energy. Yes or no?
Yes, sir.
Kinetic energy is maximum when potential energy is minimum. Potential energy is minimum at theta is equal to 0 degree. Yes or no?
Yes, sir.
So I can do the same log may. Here I have applied log may from 1 to 2. Now I can apply log may from 1 to 3. 3 position is the position of stable equilibrium or the point where the angle is 0. So I can apply log may from 1 to 3. Yes or no?
Yes, sir.
Energy at point 1 plus kinetic energy at point 1 is equal to will be equal to potential energy at point 3 plus kinetic energy at point 3. Yes or no?
Yes, sir.
This is minus mb into cos of 120 plus 0 will be equal to minus mb. Cos of 0 is 1 plus ke. Yes or no? Plus k3. Kinetic energy at point 3 will come as 3 by 2 mb. Do we understand this?
Yes, sir.
Last question now. I will ask you this one. Will it perform SHM or oscillation or periodic motion? And what will be the amplitude? Can anyone tell me this now from what we have studied? Yes, my dear friends. Yes, my dear friends. Third part. No one knows it? No one knows it, bacha? Tell me you don't know it, so I'll do it. No one has any idea? Will it be SHM or not? Will it be oscillatory? Will it be periodic? Yes?
No idea, sir.
What is the difference between periodic motion, oscillatory motion, and simple harmonic motion? Can you tell me that? Can anyone tell me what is a periodic motion? What is a periodic motion? Tell me fast. What is a periodic motion? Fast, fast. What is a periodic motion?
Repeats at regular intervals, sir.
A periodic motion is a motion that repeats at regular intervals. Correct. What is an oscillatory motion? What is an oscillatory motion?
To and fro motion.
Flow from a fixed point.
To and fro motion. Well done. Okay. Oscillatory and this one no. Is simple harmonic motion periodic? Yes or no?
Yes,
Is
sir.
simple harmonic motion periodic? Yes or no?
Yes, sir.
Is it oscillatory?
Yes, sir.
Great. Then what makes it special? It is periodic, it is oscillatory. What makes it more special? The force acting on the particle is directly proportional to x. Yes or no? That makes it special. Yes or no?
Yes, sir.
Or if I talk about angular SHM, the torque acting on it is directly proportional to theta. Yes or no? Yes or no? Yes or no?
Yes, sir.
So if you can prove that the force acting on the particle is directly proportional to x, it means that it is a simple harmonic motion. Yes or no?
Yes, sir.
If you can still also prove in case of angular SHM that the torque is directly proportional to theta, that motion will be SHM. Now the question is this motion SHM? Is this motion periodic? Of this dipole, is it periodic? Is it periodic?
Sir.
Yes, it is periodic. Don't know what you have learned. Yes, this is periodic. Is this oscillatory? Yes, this is oscillatory. Is this SHM? No, it is not SHM. Why it is not SHM? Because torque is mb sine theta. It is proportional to sine theta. It is not proportional to theta. For very small angles only it is proportional to theta. Here there is no small angle. Angle is 120 degrees. It is not small. So we cannot say that the torque is proportional to theta. And therefore, this gentleman, this motion is periodic, oscillatory, but it is not simple harmonic. What is the amplitude? From wherever I start the motion, it will go to the same point on the other side, and then it will come back, and this motion will keep on repeating unless and until there are some resistive forces which stop this motion. This motion will keep on continuously happening. The amplitude of motion is 120 degrees. Note this down. For motion to be simple harmonic, force must be proportional to minus x, or torque must be proportional to minus theta. Minus x means it has to be in the opposite direction of displacement. Minus theta means it has to be opposite to the direction of angular displacement. Do we understand this? Do we understand this?
Yes, sir.
Please note it down, sir. I'll give you 2 minutes. Let me know once you are done. Okay, then we move ahead. Remember the heading for the class, for today's class, and heading of this chapter was magnetic effect of current. But we were still dealing with the magnetic field, and now we'll move on to this magnetic effect of current, or what we call MEC. MEC in short, magnetic effect of current. Now, what is this magnetic effect of current? We have seen that a bar magnet produces magnetic field. The same effect, the same magnetic field can be produced by a current carrying wire. A current carrying wire can also produce magnetic field. A current carrying wire can also create magnetic field. And it was discovered by a scientist, Hans Christian Ørsted, in the year 1820.
Sir,
Yes, beta?
your screen has paused, sir.
Okay. A current carrying wire can produce magnetic field, and this was observed by the scientist Ørsted, Hans Christian Ørsted, in the year 1820, so far back, and that is known as the Ørsted experiment. So what is this Ørsted experiment? He had a current carrying wire. He had a current carrying wire and he had a magnetic needle. Do you understand magnetic needle? Yes or no? Do we understand magnetic needle? Yes or no? A magnetic needle or magnetic compass is basically a device which can help us in finding out the north and south direction on Earth. Because your Earth is also a magnet. Have you heard this? Yes or no?
Yes, sir.
This magnetic needle is nothing but a small short magnet, and this get deflected because of magnetic field of Earth. It can also get deflected because of any other magnetic field which is present, and that is what Ørsted found out. He had a current carrying wire. Do you see a current carrying wire here?
Yes,
This
sir.
is a current carrying wire I. When he brought a magnetic compass or a magnetic needle, the magnetic needle deflects. The magnetic needle deflects, and that made him understand that a current carrying wire can produce a magnetic field, and that is known as the Ørsted experiment. Do we understand this?
Yes, sir.
What are the observations he has done in this experiment? Observation number 1. The magnetic field that is produced is directly proportional to the current. If you increase the value of current, the magnetic field increases. Do we understand this? You also observe that this magnetic field is inversely proportional to R square. If I bring the bar magnet closer, the deflection in the bar magnet increases. That means magnetic field has increased. Are you able to understand what I'm saying here? If
Yes,
the
sir.
direction is reversed, the deflection in the needle or magnetic field is reversed. That means the direction of magnetic field is also determined by the direction of current. I'll give you 1 minute to note this down. Then I'll give them point wise so that everything is there in your sheet. Let me know once you have done. Okay, then we can move ahead and you can write some points, some facts. Just a revision of all that we have done. The first thing that you must understand is this. First, listen to me, then I'll give you time to write. A magnet at rest will produce a magnetic field. Electric charge at rest produces an electric field. We understand this? Yes or no? We understand
Yes,
this,
sir.
beta? Okay. Second point. I'll first give you all the points and I'll give you time. You can note it down. A current carrying wire produces a magnetic field, but not an electric field. So remember all these facts. On the other hand, a charge moving with uniform velocity produces electric as well as magnetic field. Remember all these points because they may come as questions in your JEE main, and I've seen a couple of questions based on this. Next point. Whenever this current carrying wire produces a magnetic field, no poles are produced. It does not create a north and a south pole like a magnet, but it shows properties of pole because it is creating a magnetic field. It shows polarities, it shows the properties of pole, but actually no poles are created. Do we understand this? Do we understand this, bacha?
Sir, your audio,
Sir, your
Okay.
your audio is very laggy, sir.
An oscillating or an accelerated charge produces EM waves. That is the last topic. Is it clear now? Let me put it here. Is it clear now?
Yes, sir.
No, sir. Once explain again, sir. We could not hear.
A magnet at rest produces magnetic field. Electric charge at rest produces electric field. We understand this?
Sir,
A current carrying wire produces a magnetic field and not an electric field. But a moving charge with uniform velocity, charge moving with uniform velocity, charge moving with uniform velocity, it produces magnetic field as well as electric field.
then your audio is very laggy, sir.
Can't help it. Let me change the connection and see if it helps. Okay, it got connected here. 5G. Just give me a minute.
Sir.
Why does it just get disconnected? Oh, oh, oh. Just a second, beta. So what I was saying is, if a charge is moving with a uniform velocity, it produces both magnetic field and electric field. We understand this?
yes, sir.
If a charge is oscillating or moving with an acceleration, that would be the last topic that we will do whenever we get to that. It will produce a EM wave, electromagnetic wave. This is how electromagnetic waves are produced. A current carrying wire does not create a pole. It creates magnetic field, but it does not create a pole. But this wire shows the properties of a pole. Do we understand this?
Yes, sir.
Okay, now I'll give you 2 minutes. Note it down. Everything is okay now? My voice is coming clear?
Yes, sir. It's okay, sir. It's okay, sir.
Okay, okay. Please note it down. So, what we are going to do now, we have already seen the field created by a magnet. We are now going to see the field created by a wire. Now to get into that, let us first write the meaning of, let us try to understand the meaning of this current carrying element or a current element. What is this current element? Have you heard this term current element anywhere?
No, sir.
It's nothing, it's just a hypothetical term that we have created so that we can understand the magnetic field created by this. We take a very small segment DL of a conductor carrying current I, and we call that element, that small length of the wire, as a current carrying element or a current element. It's just a hypothetical term just to understand the concept of how this wire creates a magnetic field. So we have created this hypothetical term. Suppose you have a current carrying wire. You can see a current carrying wire here. It is carrying a current I. Do we see this? We take a
Sir.
very small length of this wire, which is your DL, and you multiply this I with DL. Multiply I with this DL, and this DL is a vector actually. And the direction of this DL vector is same as the direction of current. Remember, we cannot call current as vector because current is treated as a scalar quantity. Do we understand this?
Sir.
So this current carrying element is nothing but the product of I with DL, and this is a vector quantity whose direction is same as the direction of current. It is a very, very small segment of a current carrying wire, and whatever formula we have devised is based on this small current carrying wire, small element of the current carrying wire, which is known as the current element. We understand this, yes or no?
Yes, sir.
I'll give you 2 minutes to write it down. Remember, it's a vector quantity. So since we have seen what is the current carrying element, remember this current carrying element plays a very important role in what we are going to do next. And what we are going to do next is known as the Biot Savart law. Ever heard this? Biot Savart law. Any idea what is this? Huh? So you can see from my revolutionary drawing what I have drawn. Huh? What I have drawn. What I have drawn.
Element.
I have drawn a current carrying wire, and then I have marked a small element of length DL. So this small element of length DL actually becomes your current carrying element. Yes or no?
Yes, sir.
Now I have a point which is at a distance R from this current carrying wire, current element I must say, and it makes this radius vector. This is also a vector which is drawn from the element to the point. Do we understand this? Here there are
Sir.
3 vectors. Can anyone tell me what are those 3 vectors? There are 3 vectors. One vector is dB vector. dB means small magnetic field. One is R vector, and one is the current carrying element vector. Do we understand this?
Sir.
Biot Savart, what they did, they discovered that the small current carrying element will create a magnetic field dB that is directly proportional to I. If I want to write it as I, it is directly proportional to DL, and therefore it is proportional to IDL or current carrying element. Do we understand this? This dB is inversely proportional to R square. Everyone following me, yes or no? And this dB is also proportional to sine theta. If theta is 0 or theta is 180, the magnetic field actually becomes 0. They put all of these things together. And they had the formula for magnetic field dB created by this small current carrying wire. It is given by mu naught by 4 pi I dl sine theta by r square, and that becomes the most revolutionary formula which we will do for the coming 5, 10, 15 days, whatever are remaining. dB is mu naught I dl sine theta by 4 pi r square. Now remember, I call this formula as the scalar formula of magnetic field because it only gives me the magnitude of magnetic field. Do we understand this?
Sir.
There is a vector formula of magnetic field as well, and the vector formula of magnetic field dB looks like this: mu naught I by 4 pi I into dl cross r divided by r vector or r cube. I can write it like this also. Let's not make it very confusing. This becomes the vector formula of magnetic field. We might not be using it, but it is important that we understand this is the vector formula of magnetic field. Therefore, it gives us both magnitude as well as direction. Do we understand this?
Sir.
But the upper wala formula, the first formula is the scalar formula. It only gives us the magnitude. How do I get the direction? I get the direction of magnetic field from the cross product. The direction of magnetic field is given by the direction of dl cross r. We will try to understand this direction in the next class. The direction of this magnetic field is given by the direction of dl cross r. So basically, which formula are we going to use? The formula that we are going to use is the first one, and we will find out the direction of magnetic field by dl cross r. Do we understand this? Do we
Sir.
remember cross product, anyone?
Sir.
The direction of magnetic field, I must write here, the direction of magnetic field dB is perpendicular to both the dl vector and r vector. Do we understand this? Do we understand this?
Yes, sir.
In this particular case, it will be going inside the plane of the paper. Inside the plane of the paper will be written by cross. Outside the plane of the paper will be written by dot. We will understand this cross and dot in the next class. I'll give you 2 minutes. You can note it down. And then we will wind off the class here because we'll have to understand this formula. So I have given you this formula. You can go through this formula, and then from this formula, we are going to write some results. We're not going to derive them. There is no point of deriving them. We're going to write some results, and hopefully in the next class, we will be way ahead in our understanding of magnetic field. Up till now, everyone has understood this?
Yes, sir.
Everyone is clear? The concept of magnetic field is clear. It moves in loops. Everyone is clear with that? Everyone understands the concept of current carrying element? Yes or no?
Understood, sir.
Okay, then we will go ahead with this in the next class. Anyone has any doubt? Please come up. Else the class is over from my end. Take care and God bless you.